We are back with another lesson. In this lesson, we'll discuss diffraction at single slit. So, in this topic, I will explain the phenomenon of diffraction of light at a single slit to show the formation of diffraction fringes. Fine. So, consider you have a source of light S. Fine. This source is producing light waves in all directions. Fine. Now, let us say we focus the light produced by this source using a convex lens. Fine, so we will introduce a convex lens to focus the light produced by the source S. So, the rays produced by the source S is focused by a convex lens to pass through this slit S. The size of this slit, okay, let us assume it to be of size small d. Right? Now consider, let us name this slit as your slit AB. Let this point be A, let this point be B, and let the center of the slit be C. Right? So your rays represents a wavefront. Let us assume this rays to be your plane wavefront. Fine. So it seems this is your plane wavefront. This wavefront is incident on the slit AB of size small d. Fine. So this is how it will look. You have a plane wavefront incident to your slit. Fine. Now as soon as they are incident on the slit, what happens? Each point So each point on this slit will act as a source of your secondary wavefront. Fine. So from this secondary wavefront, the new waves will be produced. Fine. So the new waves will be produced from this slit AB by using your Huygens principle. Now let us say those waves, the new light waves or your secondary wavelets produced, let us focus those waves on a screen. Fine. On the screen using another convex lens. Okay, so let us focus this light waves produced from the slits at a point O on your screen. Okay, so you have focused the light passing from this slit at the point O on your screen. Let me draw the directions. Okay, so now if you notice the light coming from your point A and the light coming from your point B, they are traveling the same distance. In such case, when the light is traveling the same distance, so in this case there will be no path difference. If there is no path difference between the light waves, that means there is no phase difference. If there is no phase difference, then at the screen the two waves will interfere constructively to produce a maxima. You will produce a bright fringe at your point O, and this bright fringe will be known as your central maxima. Okay, so this is how it will look. The wave, let us divide the slit, okay, this slit into 12 points. So the wave coming from this 0 and the wave coming from this 12, they are in the same phase. Fine, they are in the same phase. So at this point they will interfere constructively. Similarly, consider the wave coming from this point 2 and the wave coming from this point 10. they interfere again constructively. Similarly, consider your pair 4 and consider your pair 8. Again, the wave travels the equal path difference, the wave travels the equal path, therefore they will be in phase with each other, and the waves traveling 6, okay, it goes and it strikes the point O. So at the point O you will get a bright fringe, okay, you will get a maximum intensity light, fine, and this point O will be known as your central maximum. Okay, so you will get something like this bright spot. Can you see this one? Okay, this is your central maximum, fine. Fine. Now, apart from this rays, there will be also rays which will be traveling in some other angle. Okay, so let me just rub this two rays. Fine. Now, consider another set of rays. Okay, let's this be a set of rays. Now, these rays are moving at an angle theta with respect to your previous one. Fine. Now, what will happen after this rays? They are passed through your lens L2. They will be made to be converge at this point. Fine. Now, in this case, let us consider the point where they converge as point P. Now, look here. The distance traveled by the light, which starts from this point A, this distance, and the distance traveled by the light, which starts from the point B, this distance, are they same? No. In the case of this one, your third ray, when it starts from your point B, what happens? The light has to travel a extra path difference. To show the extra path difference, what you can do is you can draw a perpendicular line on this third ray. Draw a perpendicular line. Let us say this perpendicular as your A N. Fine. Your AN is perpendicular. Okay. So if you consider the ray, if you consider this distance and this distance, they are same, equivalent. So the extra path traveled by the ray starting from the point B is this one. Fine. Fine. The one which I have drawn with green pen. Okay. Can you see? This is the extra path travel. So in such case, where there is a extra path difference coming into the picture, if there is a path difference, what will happen? The rays which are appearing at this point P, this one and this one, they will have a phase difference between them. And if they have the phase difference between them, then it will result into a constructive or your destructive interference. Fine. Now, now look here. If you consider the extra path travel to be lambda, this extra path difference travel to be lambda. Fine. Okay, this is the extra path difference is the distance equivalent to one wavelength. Now, what you can do is consider this slit, okay, into two halves. This is your first half, this is your second half. So consider this distance. So this distance will be half of this distance. Fine. This distance is half of this distance. That means this distance is how much? Lambda by 2. Since this point 6 represents the half of this slit, and we have divided slit into two parts, part 1 and part 2. Right? This is half of your wavelength. Okay. So if the extra part difference is lambda by 2. Okay. So at this point 0, okay, there is no part difference. Okay. Consider a light, or you can also see it like this. consider a light which starts from this point A. It moves. So consider a light starting from this point A. Okay, so it moves one wavelength, two wavelength, three wavelength, four wavelength, and five wavelength. Fine. Similarly, the light which moves from this point A. Okay, consider from this point. Okay, consider from this point. So look, one wavelength, two wavelength, three, four, and five. So since this distance and this distance are same, so light is traveling five wavelengths. But in this case, there will be a extra wavelength traveled. Why? Because of this extra lambda by 2. Fine. Can you see? There will be a extra portion. So in this case, at the point C, the light has traveled an extra path difference of how much? Lambda by 2. Fine. So similarly, if you consider your point 2 and your point, consider your point 2 and your point 8. Okay, there will be an extra path difference of lambda by 2. Similarly, consider your point 4 and your point 10. There is an extra path difference of lambda by 2. Similarly, consider your point 6 and your point 12. There is a extra path difference of lambda by 2. Can you see? In this case, 1 lambda by 2, lambda by 2. But in this case, only lambda by 2. Fine. Fine. So let's look what happens when a path difference of lambda by 2 is there. Okay. Suppose this is one wavelength, lambda, and consider the light coming from this point 6. The light coming from the point 6 has a extra wavelength, lambda by 2. Fine. Now, in this case, if you compare, okay, when it reaches your point P, what will happen? Can you see? The crest and the trough will interfere with each other. If the crest and the trough interfere with each other, in such case, at this point P, whether will you get a bright fringe or your dark fringe, you will get a dark fringe. Fine. So I can say when the path difference is how much? Lambda. When the extra path traveled by the light is how much? Lambda. In that case, at this point P, you will get a destructive interference or you will get a dark fringe. Fine. Fine. So this point P will represent your first secondary minima. The same condition will be followed here also. If the light is moved in the other way direction, if the light is traveling like this, fine. In that case also, if the path difference is lambda, you will get a first secondary minima. So up till now we have discussed about your central maxima and we have discussed about your secondary minima. This is your secondary minima. Fine. Now, if this central maxima is your primary maxima, okay. Next, again at this point you will get a bright fringe. Fine. Now that bright fringe we will call as first secondary maxima. Fine. So let's see how we'll get a maximum here. Light will get a fringe of maximum intensity here. Fine. Now consider another set of three rays which are bent further away from your original axis. Fine. Now let me introduce a glass lens to focus these three rays on your screen. Let me introduce a convex lens here. Fine. So after introducing your second lens L2, the lens will focus at this point. Fine. Now in this case, again let us give this point some name. Let us consider this point as P. Fine. Now again, if you look properly, the light which starts from this point A and the light which starts from this point B. Okay. What happens in this case is that suppose if the light is bent at this much angle theta. Fine. Now consider you draw a normal an. Fine, this is your normal. Okay, now again, if the light started from this point and if the light started from this point, in the light which goes from here and the light which goes from here travels the same path difference. But if you see in the case of this third ray, you will see a extra path difference. Fine. So let us suppose if the extra path difference is thrice of lambda by 2. Fine. Fine. This is your 3 lambda by 2. Fine. If the extra path traveled by the light coming from this point V is 3 lambda by 2. In such case, what happens? You will get a maximum at this point. Okay. To understand this, again, what you will do, just like your previous case, okay, you will divide the slits. But instead of dividing into two halves, now what you'll do, you divide it into three halves. One, two, and three halves. Fine. So light which starts from here travels an extra distance of 3 lambda by 2. Light which travels from here travels an extra distance of lambda. Fine. And the light which starts from here, the light travels an extra distance of lambda by 2. Fine. This is lambda by 2. So now if you look carefully, okay, consider your light coming from your first and your second half. Okay, consider only this two half for now. Fine. From this two half, consider the light approaching from this point A and the light approaching from this point 4. So consider the light coming from the point O. 1, 2, 3, 4, and 5 wavelength. Similarly, the light coming from the point 4. Okay, consider the light coming from this point 4. 1, 2, 3, 4, and 5. Fine. So up till this point, the light travels equal path. So there is no path difference. But if you notice for the point 4, there is a extra path difference coming into this picture. Fine. Just like your destructive interference, there was a extra path difference into coming into the picture. And how much was the path difference? Lambda by 2. Let me go back. Okay, yeah. See, there was a extra path difference coming into the picture. And how much was this path difference? Lambda by 2. If the path difference lambda was by 2 was coming into the picture, then the two waves interfere destructively. Fine. The same case will be observed here also. There is an extra path difference of lambda by 2. So the two waves will interfere destructively. Therefore, at this point P, the resultant of this, the light coming from point 0 and the point 4, will cancel each other and you will get no effect. Fine. But what about this third half? What will happen is that now see this two light has cancelled each other, but the light coming from this third, consider the light coming from this point 8. It travels one wavelength, 2, 3, 4, 5, and 6. Fine. So the light coming from this point 0 and point 4 cancel each other. But what will happen? The light coming from this point 8 will go and contribute at this point P. Therefore, at this point P, you will get a bright fringe. And this bright fringe, so at this point P, you will get a bright fringe. Fine. And this bright fringe will be known as your first secondary maxima. So at this point you will have your first secondary maxima. The same condition will be followed here also at down. At this point also you will have your first secondary maxima. And the maxima which is at the center is known as your central maxima. Fine. So this is your central maxima. This is your first secondary minima. This is first secondary maxima. This will be your second secondary minima, and then so on. Fine, this will repeat so on. Similarly in down part. Okay, so from here we have discussed how the diffraction produces your interference pattern. Okay, and one more important point. Okay, now if you look in the case of your central maxima at this point O, all of the light are contributing. Can you see? All of the light, they go and contribute at this point O. So at this point O, you have the maximum bright spot. Can you see? It is very bright as compared to this one, this one, this one, this one, this one. Can you see? So it has the maximum intensity. Fine. So as you go to your first secondary maxima, okay, if you go to your secondary maxima, what happens? The light coming from this first 1 by 3rd part of this slit, okay, this is being cancelled by the light coming from this second portion. The only part which is contributing is your third portion. So if only third portion, that means how many points are contributing? Look, it is this point, this point, this point, this point. Only this much point is contributing to give your secondary maxima at this point. Therefore, the intensity decreases at this point. Fine. So what you notice is that at the center you have the maximum. Fine. But as you go away from the center, you will still get a constructive interference, but the intensity will be smaller. Can you see? This is the intensity curve. On the y-axis, it represents your intensity. On the x-axis, it represents the position. So as you move further away from the center, the intensity, can you see? It decreases, and it will keep on decreasing further. Fine. So this is your intensity curve. Fine. But whereas your this dark fringe, okay, this represents your destructive interference, where the two waves cancel each other, the wave coming from the first half and the wave coming from your second half. In this case, the wave coming from the first half cancels the wave coming from your second half. Right? So in this case, in the such case, what will happen? You will have a destructive interference. Therefore, at this point, you will have the minima. Fine. But the minima will be same. Okay, because for minima, we don't consider intensity. Fine. The intensity is 0. So for this diffraction, okay, for this diffraction, in my next class, I will derive the I will derive the, first I will show the equation of the path difference. Okay, this extra path which the light has to travel. First, we will derive the equation of this path difference for your destructive interference as well as your constructive interference. Fine. Then we will find the position of your secondary minima and your secondary maxima. Fine. Okay, so that's all will be your for the diffraction. Okay, for diffraction, you can remember the derivation part. Okay, just the derivation part which I'll do in my next class, and you can remember the intensity curve. Find this intensity curve. The rest, these portions are just for your concept part. Okay, these topics are not that much relevant as compared to from the board's perspective. Fine. The only thing important is the position of the maxima and minima, the position of your minima, the position of your maxima, the graph for the intensity, fine, the graph for the intensity, and what will be the width of this central maxima. Fine. That's all important for the board perspective, okay, which I will be doing in my next class. Fine. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So again, thank you.